Swayam Prabha. Digital India. Educated India.
Hello students, in this lecture you will be acquainted with some unique physicochemical properties that emerge at nanoscale. So, we have already discussed size effects and surface to volume ratio in our previous lecture. So, we will be discussing some other emergent properties like optical properties, magnetic properties and thermodynamic properties of nanomaterials. So, I have already discussed this in my previous lecture that properties of nanomaterials change drastically when as their scale changes from bulk material to nanoscale. So, I will not discuss these things in detail again, but let us make a quick revision. So, reduction of materials to dimensions 1 to 100 nanometer makes a property change, and the properties change into there are some unique effects that are observed like quantum confinement and a large surface area to volume ratio and surface forces getting dominant. So, all these things result in unique properties that arise at nanoscale. The nanoscale is a comparable length to electrons, photons in biomolecules. So, breakdown of classical bulk behavior happens, like bulk materials behave in a different way. So, they are broken down into smaller molecules. So, breakdown of classical bulk behavior happens. Then there are dominance of quantum and surface phenomena. So, all these things I have already discussed in detail in my previous lecture. Like some dominant forces like bulk properties, gravity and inertia dominate in bulk materials, and surface forces dominate in nanomaterials like hydrogen bonding and other surface forces like van der Waals forces and surface tension. So, surface forces dominate in this nanomaterial and bulk forces dominate in bulk material. So, we have also studied quantum confinement effects, high surface area to volume ratio and dominance of surface forces. Let us just make a quick revision. A large fraction of atoms are at the surface, leading to increased reactivity when the surface to volume ratio is high. Quantum confinement, where electrons become confined to discrete energy levels, altering properties, and dominance of surface forces, where surface forces dominate over bulk forces like gravity and inertia. So, all these things we have already studied. Okay. Quantum confinement effects, where electron motion is restricted in one or more dimensions and discrete energy levels replace continuous bands. Then band gap increases with decreasing particle size, and this is the basis of quantum dots and nanoscale optoelectronics. Then high surface to volume ratio, where large fraction of atoms are located at the surface and surface atoms have unsatisfied bonds. There is enhanced surface energy and reactivity, and this is a critical factor for catalysis and sensing. And then surface chemistry at nanoscale, surface dominates the physicochemical behavior. There is easy chemical functionalization with ligands and molecules because of their size and surface behavior. Then stability and dispersion controlled by surface coatings. The stability and dispersion of nanomaterials can be controlled by various surface coatings, and this is a key principle in nanobiotechnology design. So, surface defects are in nanomaterials are structural or chemical imperfections that occur at the surface layer, where the regular repeating pattern of atoms get disrupted. Now, because nanomaterials have an exceptionally high surface area to volume ratio, these defects exert a much more influence than they can in a bulk material. So, these surface defects can arise due to various reasons. They can arise due to an incomplete coordination of surface atoms. So, crystal lattice ends at the structure, it creates dangling bonds or unsatisfied bonds, and the surface atoms have fewer bonds. These are known as dangling bonds. Okay. So, that results in a surface defect, or second, that there can be a surface reconstruction where atoms shift from bulk positions to minimize surface energy. So, as we already know that most of the atoms in nanomaterials are located on the surface. So, atoms start to shift from bulk positions to minimize it. So, the more surface atoms on the in a material, and there is more surface energy. To balance out that surface energy, the atoms from the bulk positions try to minimize the surface energy by coming in between. So, that creates some some reconstruction and defects happen. Or there can be vacancies or interstitials near the surface where missing atoms or extra atoms create localized stains. Then there can be adsorption of foreign species like oxygen water surfactants can bind to surface atoms, and if something binds to a surface atom, their entire chemistry changes and defects in the lattice will be observed. Then the defects can be due to various synthesis conditions which create high energy sites or steps. Then it can be due to mechanical or thermal treatment where deformation happens, or annealing can generate steps, kinks and terraces. So what are these things? We'll discuss it in detail in the next slide. So there are various types of surface defects. Vacancies, interstitials and atoms, these are all zero dimension point defects. Zero dimension point defects because it's like one atom missing. In vacancy, there's a missing surface atom. So the example is that it can serve as an active site for catalyst. Okay. In interstitials, an extra atom is lodged between the surface atoms. So vacancy is like there's an atom missing. Okay, there's an atom missing there's on the surface and it is vacancy. In interstitials, an extra atom is lodged in the surface, okay, which distorts the local lattice. In atoms, atoms are adsorbed on the surface. These are all point defects. Then there can be line defects like steps and kinks and dislocations. So steps are one atom high ledge, like you imagine a step. So that's a one atom high ledge, and kinks are basically over here, and step is basically over here. Then there can be a terrace or a grain boundary. In grain boundary, there can be two different interfaces interacting, and because of that, there is a whole planar defect. So these are two-dimensional defects. So there are examples of this. Like for vacancies, vacancies can be exploited as an active site for catalysis. Interstitials can distort local lattice, and atoms can alter surface energy and electronic states. Steps can be high reactivity sites. Kinks can be mostly chemically active sites. Terraces are often less reactive. Grain boundaries basically alters mechanical and magnetic properties, as these are surface related. And then there can be dislocation emerging at the surface which influences plasticity. These are the various types of surface defects. There can be vacancy, that is single atom missing, or there can be edge dislocation or twin boundary where two interfaces, they do not match, and then there can be voids, and these are point defects, these are line defects, these are planar defects, and that is volume defect. And these are, you can see how these are different from the crystal lattice. That's a perfect crystal lattice, and then atoms go missing and all these defects are created. So there can be point defects, that is a single atom either going missing or coming onto the surface to create some misalignment. Then there can be edges dislocation where edges are dislocated. Okay, that is line defect. Some edges get dislocated. Then there are planar defects, an entire plane is misaligned or something. So the interfaces do not interact like it happens in a perfect lattice. So it is different from the perfect lattice and a defect is created. So, or it can be void or disorder, these are volume defects. An entire volume is, you can see it is missing. So either missing or over aligned, so it's like coming over the top of it. So all these things create volume defects. These defects can be either manufactured or these are inherent. Certain defects are inherent and certain defects are also manufactured to exploit the properties. So how do you relate these surface defects versus to the particle size? So as I've already told you that most of the atoms in nanomaterial reside at the surface, so surface defects are even more prominent, because on the surface if an atom goes missing, so you can see it creates an entire disruption in the entire molecular assembly and function and structure. So how do the surface defects depend on the particle size? Smaller the nanoparticles, higher is their surface to volume ratio, and higher is the fraction of defective atoms. As you can see from the equation, the fraction of defect is inversely proportional to the radius or diameter of the particle size. So, as we can see, that very small nanoparticles are mostly defective at the surface. So, fraction of defect will be higher, small is the size of the particle and the fraction of the defect will be higher. So, you can see that more atoms are on the surface, so fraction of defect will also be higher. Size effect, I have already explained certain size effects, and physical and chemical properties depend very strongly on the particle size, you already know. So, certain other properties I will be explaining, like melting point depression in nanoparticles, the thermodynamic properties, the optical absorption and emission, and magnetic and electrical properties that get altered at the nanoscale. So, I will be discussing these one by one. Let us start with elasticity, elastic properties or elasticity. So, elasticity describes the reversible deformation of a solid upon applied stress, and it is measured by Hooke's law. We have already studied elastic properties for bulk materials. So, here also the equation is almost the same with a slight change, that is the Hooke's law. According to the Hooke's law, stress is directly proportional to strain. Okay, stress is E times strain, but here it is like here the Young's modulus is basically size dependent Young's modulus. We will discuss what size dependent Young's modulus is in the next slide. So, basically a large fraction of atoms lie at the surface. So, surface atoms have lower coordination number, and surface stress and surface energy modify these interatomic forces, and internal pressure and lattice strain become size dependent. So, according to the equation, stress and strain are interrelated by the size dependent Young's modulus now instead of the normal Young's modulus. So, how does the Young's modulus depend on the size of the material? This is the expression for size dependent Young's modulus, which is directly proportional to R, where R is the nanoparticle radius. So, E bulk is the bulk Young's modulus, C is the material dependent constant that is related to surface energy, and R is the nanoparticle radius. So, this is the size of the material, and so this depends on this with a direct relation. So, as the size decreases, the Young's modulus also decreases. So, as R decreases, surface effects start dominating and elastic softening happen. So, more the Young's modulus, harder the material, less the Young's modulus, lesser the Young's modulus, the material is soft. So, we can see that there is an elastic softening for many metallic nanoparticles. These are softer and hence easy to manipulate. So, hardness decreases as we go down to the nanoscale. That's an experimental graph showing Young's modulus versus grain size of polycrystalline graphene with random size grains and regular size grains. So, that is the grain size on the x axis and Young's modulus on the y axis. You can see the direct relation of random sized and regular sized nanoparticles. So, as the grain size, you can see grain size increasing, Young's modulus is increasing, and hardness goes increasing like this. So, smaller the particle, lesser the Young's modulus, and softer the material. There is also a combined effect. There is also a combined effect of size and porosity in nanoparticles. Elastic modulus depends both on particle size and porosity. So, it also depends on porosity in the same way, and it has a direct relation with porosity. So, more the porosity, softer the material. Okay. There is a surface softening due to porosity also. So, more porous the nanomaterial is, the Young's modulus is lesser. So, there is also softening or stiffness reduction. So, your particle size is smaller, your Young's modulus is also less, and there is an elastic softening, the softer the material, and your nanoparticle is more porous, your Young's modulus is again less, and there is also a surface softening. In this case also the material is softer, hardening is reduced. Melting point also differs at nanoscale because, as you know, most of the atoms reside at the surface, and there are the surface energy is very high, and it is different that from the core. So, a melting point depression happens. Melting point depression is basically drastic change in the melting point of the material. So for nanoparticles, the melting point is significantly lower than that of bulk material, a phenomenon known as melting point depression. So melting point of nanoparticle is less than melting point of the bulk material, which is calculated from the Gibbs-Thomson equation, which is represented by the Gibbs-Thomson equation. This is a modified form of the Thomson equation, where this Tm is the melting point of the nanoparticle of some radius r, and this is the bulk melting point, and that's the equation of gamma SL is the solid liquid interfacial energy, and that is the density of solid, and L is the latent heat of fusion per unit volume. So this is the equation, and you can see as the particle size decreases, the melting point also decreases. It can melt faster. There is a direct relation between melting point and the size of the particle. Then there are optical properties. In optical properties, we will be discussing local surface plasmon resonance in metal nanoparticles. We will discuss it in detail what this is. This is a very important property that has been exploited in bioimaging and in LCD screens. So there is a strong light absorption scattering, color changes with particle size and shape, as I have already told you, that is because of quantum effects, and these we will be discussing. So let us start with photoluminescence. So as because of quantum confinement, as the size reduces, the energy gap between the valence band and conduction band increases. So it's like this. As the particle size decreases, the energy gap between the bands become more discrete, and the energy gap increases. So photon falls upon this particular electron and it jumps to a higher energy level. So when it falls back to the ground state, it releases a high amount of energy, which is basically photoluminescence, and this differs, photoluminescence differs according to the size and shape of the material. So a photon falls upon this and electron gets excited and it goes from valence band to the conduction band, and these are discrete energy levels or quantized energy states, and this emission is happening over here, and the band gap you can see is narrowing. Red light, band gap is more. Blue light, it is a higher energy lower wavelength, and red, that is, you can see from this picture, no, red, that is higher wavelength, and blue, that is lower wavelength, and hence high energy and lower energy. So that is the particle size correlating with the wavelength. So PL is the first thing that we measure in a nanoparticle. It tells a lot about the size of the particle, and the range where it reflects light shows the particle size and also the elements that are present. So that is normalized PL, that is upon UV excitation and depending on the core size. Now it is localized surface plasmon resonance on plasmonic nanoparticles. Surface plasmon resonance basically happens when in a semiconductor metal, light falls, an incident light falls upon it, and electrons start to oscillate in unison. The electrons start to collectively oscillate in unison, and this happens when an incident light strikes upon the material. Now when the frequency of this incident light matches the frequency of the oscillating electrons, they start to resonate. Okay, so when they resonate, they absorb that energy, and hence the optical properties are very different. So when you consider an electron, basically it is already confined, it does not have that much of space to move and oscillate, so there is a localized surface plasmon resonance. Its resonance is basically localized, it starts to oscillate in one position. So that causes localized surface plasmon resonance, and it depends on the wavelength of light that strikes upon that material. So it is dependent on the wavelength of light. So you can see, and the surface exposure. Basically, if there is a spherical particle, this is a square and this is a triangular particle, and you can see on the edges how beautifully it is radiating. So this happens because of localized surface plasmon resonance of nanoparticles. So you can see basically the surface plasmon resonance is localized. These are silver and gold nanoparticles of different shapes and sizes, you can see, and hence they give off different colors. So this is a very interesting property of nanomaterials, the optical property that is utilized in many LCD screens, where vibrant colors are created to mark the difference. You can see silver nanoprisms, which is 100 nanometer, then that is gold spheres of 100 nanometer, then gold spheres of 50 nanometer. See, just 50 nanometer difference, and from orange to green. Then silver spheres 120 nanometer and 80 nanometer, and you can see the color difference that much, and that is the electron microscopy images of these particles. That's the example of size dependent optical properties of quantum dots. These are semiconductor nanoparticles and the fluorescence emission. So that's the emission for red light, that's the emission for blue light, depending on the particle size, excitation, band gap, and when the particle is large, the band gap is smaller, and when the particle is small, the band gap is larger. So these properties have been used in various bioimaging and biosensing techniques. So there can be sensing domains like antibodies, aptamers, all these are of the nano size. So you can integrate these with the nanoparticles and they become bio nanoparticles. And now there is a high specificity for these bio nanoparticles with the you are integrating this with an antibody. There is a high specificity for this, and basically the antibody is integrated with the nanoparticle, and these have a high specificity for their detection domains, like whatever antibody is will require that particular antigen, and they will combine and give an amplified signal of this, and that is how you bioimage and biosense things. So biosensors are made in this way only, like the HCG kits and all. So basically nanoparticle is being integrated with these antibodies which are highly specific, or aptamers or ligands and enzyme things, you can do that also. Then there are fluorophores. So there is a high specificity for that. You integrate that with a nanoparticle, and then these combine with their detection domains and cause they give off a signal, and signal when amplified can be detected. So nanoparticles also have some unique magnetic properties, like I have already told you before. There is super paramagnetism, which I will be discussing in my next slide. So there is absence of magnetic hysteresis at very small sizes, which is a very unique property, and then I will be discussing about hysteresis loop and the difference that happens at nanoscale. Then there are the applications. Due to magnetic property change, it has a huge scope in data storage and biomedical fields. Let's understand first what is magnetic anisotropy. So magnetic anisotropy is change in the magnetic property of a material. For example, let's say how easily a magnet is magnetized depends on the direction you cause the magnetization. Like you put a field in one direction and it has a certain magnetization, and you change the field and the magnetization is not the same. So the property gets differed. So in simple words, magnetic anisotropy means a material's magnetic properties change depending on the direction you measure them in, unlike a perfect sphere where it is the same everywhere. It is like having easy and hard directions for magnetization. That is, materials prefer to magnetize along certain easy axes. Materials prefer to magnetize in certain hard and easy axes. So it can be due to various reasons, like atoms in a crystals align in specific ways, making some directions in the lattice better for magnetism. It can be shape anisotropy, meaning thin needle is easier to it can be shape anisotropy, like a thin needle is easier to magnetize along the line rather than from the point. So it can be also like shape difference, shape anisotropy. Or so the applications also range from permanent magnets in motors to magnetic storage. So magnetic anisotropy, let's discuss this in detail. That's the anisotropy energy, where effective anisotropy and angle between magnetization and basically this is the angle, theta is the angle between magnetization and the easy axis, like the axis on which it can easily magnetize, and K is the effective anisotropy constant. So this is the anisotropy energy and the equation for that. In nanoparticles, what happens is that K, the effective anisotropy constant, it depends on the size of the particle. So Ks is the surface anisotropy constant and d is the particle diameter. So surface anisotropy becomes dominant as d decreases. So as the diameter of a particle decreases, smaller the particle, the more the surface anisotropy happens. So magnetic anisotropy creates an energy barrier that stabilizes and a nanoparticle's magnetization. But thermal energy helps the nanoparticle to break that barrier. So when the thermal energy basically overcomes this energy barrier, the particle enters a super paramagnetic state, causing rapid magnetization flips and zero net movement without a field. So this helps it behave like a giant paramagnet with large susceptibility but no hysteresis. That's the equation for super paramagnetism, where thermal energy exceeds the anisotropy energy. This causes magnetization fluctuation, random magnetization fluctuation resulting in super paramagnetism. So the characteristics are zero coercivity, zero remnants and high magnetic susceptibility. You will understand all this better when I explain a hysteresis loop to you. So that's a hysteresis loop. Let's understand this. This is the applied field direction. You apply magnetic field in this direction and magnetization goes on to increase till a saturation point. And then you stop this field and it will fall back, although not down to the zero, but it will retain some amount of magnetism. Even though you apply a magnetic field in this direction, it won't just flip to zero. It will retain certain amount of magnetism. And then you apply a magnetic field in this direction and it will fall back to zero. And this is basically the coercive field, the amount of magnetic field that is required for reverse magnetization. Then you again apply a field in this direction and then again then a field is applied in this direction and then from 0 to a saturation point in this direction, and then you switch it off and then again there is some remnant field and at this point and then applied field in this direction and then again to this point. So there is certain magnetic remnants that is being shown by materials because of magnetic anisotropy that I have already told you. So this causes magnetic lags. You cannot just switch it on and switch it off, but what happens in nanoparticles is that super paramagnetism is observed where thermal energy exceeds the anisotropy energy, and what happens is that the thermal energy dominates and there is almost zero remnant magnetism and zero coercive force, and it just goes down to zero and magnetization in this direction. So there is rapid magnetization and this is what happens. So this black line shows ferromagnetism and this blue line shows super paramagnetism, and that's a diamagnetism and paramagnetism. That's paramagnetism and diamagnetism. Okay. So that's hysteresis loop for you, and the area of the loop corresponds to the hysteresis loss. That is the energy loss that is created by this magnetic lag. That's the difference between a ferromagnetic particle and a super paramagnetic nanoparticle. So what happens is that there is no magnetic field and the particles are in all random directions, and super paramagnetic particles are also in all random directions. Then you apply a magnetic field and all these align in one direction. The super paramagnetic nanoparticles also align in one direction. Then you turn the field off and ferromagnetic particle align in the same direction for some time because there is a remnant magnetization that is observed over here. And then in super paramagnetic nanoparticles there is no remnant field observed, so it is like switch on and switch off. You switch it on and in one direction and then you switch it off and it just flips all of a sudden. There is no remnant energy and there is no hysteresis loss. That is the magnetic property of iron oxide nanoparticles. As you can see, these are magnetic nanoparticles synthesized. You put a magnet and all the particles in this direction. So that is the hysteresis loop, narrow hysteresis loop. There is almost no hysteresis loss, although no hysteresis loss in this. These are the applications. It can be applied in bioseparation, in biosensors, molecular imaging, catalysis, information storage. So all these are functions of magnetic nanoparticle. In MRI also it is being used. Then there are nanoscale thermodynamic effects. So there's an increased Gibbs free energy due to surface atoms. Surface atoms, as you know, they drastically increase, and they, as compared to bulk atoms, the surface atoms are higher. So there's an increased Gibbs free energy due to that, and there's lower phase transition temperatures, enhanced diffusion rates, and metastable structures become more accessible. Surface energy and total free energy. The total Gibbs free energy of a nanoparticle is the bulk free energy plus the surface energy. Surface, basically the Gibbs free energy of surface is surface energy per unit area into surface area. So as you can see that Gibbs free energy of a nanoparticle depends a lot upon the surface area and surface energy of a nanoparticle, and both increase as the size decreases. So as R decreases, the surface contribution becomes more dominant, which means the thermodynamic stability is altered. So more the surface area, more the surface energy, more is the Gibbs free energy, and more is the Gibbs free energy, less is the thermodynamic stability. So that's the equation for a spherical nanoparticle of radius r. The Gibbs free energy of nanoparticle is G bulk plus 4 pi r square gamma, where basically r is the size of the nanoparticle, r is the radius of the nanoparticle, and this is the surface energy per unit area. 4 pi r square is basically the surface area, and gamma is the surface energy per unit area. So more the Gibbs, the effect is basically, that's the equation, and the effect is basically more the Gibbs free energy, more are the surface atoms at what it causes as at nanoscale is that more surface atoms. So that's the equation, and as the Gibbs free energy goes on increasing, so because of more surface atoms there is thermodynamic instability. Then phase transition which happens due to surface energy dominance, there's the result is that there's a huge melting point depression. The melting point of a nanoparticle is drastically lesser than that of bulk material. So you can see that the phase transition also depends a lot on and then diffusion, short energy, the cause at nanoscale is short energy paths and high energy, and which results in faster kinetics. Then there are metastable phases, altered energy landscape, new material properties. So how are these properties relevant to nanobiotechnology? Nanoscale properties match biological length scales. If there is an efficient interaction with DNA, proteins and cells, there is controlled biorecognition via surface engineering. You can surface engineering things and cause this causes biorecognition. Then there is a foundation of diagnostics and targeted therapy, as we have seen via different its optical properties, magnetic properties and thermodynamic properties are utilized for all these diagnostics and targeted therapy. So we have seen by now that nanoscale materials exhibit unique physicochemical properties, and size and surface effects dominate their behavior, and emergent optical, magnetic and chemical phenomena can be seen. These properties enable advanced nanobiotechnology applications. Now let's discuss the applications part of your nanomaterials. So in 2026, the global nanomaterials market is projected to reach approximately $12.1 billion, reflecting their critical roles across multiple industrial sectors. So applications. So in 2026, the global nanomaterials market is projected to reach approximately $12.1 million, reflecting their critical role across multiple industrial sectors. So nanomaterials have various applications in multiple sectors. So in medicine and healthcare, in electronics and energy, in environmental protection, in food and agriculture, in consumer goods and textiles. So I'll be discussing these in detail in my next slides. So these are the applications, and your nanomaterials market is expected to make a boom and to reach approximately $12.1 million in 2026. So this reflects their important role across the globe in multiple industrial sectors. So that's medicine and healthcare. In drug delivery, nanocarriers like liposomes and mesoporous silica nanoparticles, these provide targeted delivery, allowing drugs to bypass the blood-brain barrier or selectively attack cancer cells without harming healthy tissues. So these are nanocarriers that are going to carry drug. So these are carriers, liposomes and mesoporous silica nanoparticles. These are nanocarriers that provide targeted delivery, allowing drugs to bypass the blood-brain barrier or selectively attacking cancer cells without harming healthy tissues. So that is drug delivery. Then diagnostics, quantum dots and gold nanoparticles, they are already being used for bioimaging, and these can also detect tumors or infectious diseases with high precision. So they can also be used in diagnostics, that is quantum dots and gold nanoparticles, these are used for bioimaging and detecting tumors or infectious diseases with high precision. Then vaccines, lipid nanoparticles are essential for delivering mRNA vaccines, while other nanoparticles act as adjuvants to enhance immune response. So vaccines, lipid nanoparticles are essential for delivering mRNA vaccines, while other nanoparticles act as adjuvants to enhance the immune response. Then tissue engineering, nanocomposites are used to fabricate artificial joints and body part implants. So these are also very useful in tissue engineering, where nanocomposites are used to fabricate artificial joints and body part implants. So these are the healthcare applications in tissue engineering. So all these kinds of tissues, these nanomaterials are useful in the tissue engineering area, and then in medical diagnostics, in MRI, PET, CT, in this zone, and then in drug delivery, they improve drug efficiency, enable targeted therapy, then improve therapeutic safety and also reduce side effects. Then in cancer therapy, enhance traditional treatments, provide novel treatments. Then in gene delivery, they protect genetic cargo, they enable precise targeting, enhance cellular uptake and overcome biological barriers. And in antimicrobial and antiviral applications, they offer innovative therapies and they reduce the risk of resistance. So these are the healthcare applications of nanotechnology in a nutshell. Then in electronics and energy, there is miniaturization. Carbon nanotubes and graphene are replacing silicon to create smaller, faster and more energy efficient microchips and transistors. So currently silicon has been widely in use. So now carbon nanotubes and graphene are replacing these silicon chips to create smaller, faster and more energy efficient microchips and transistors. So there is this miniaturization of this the silicon. There is a miniature replacement for this silicon to create faster, more energy efficient microchips and transistors. Then for energy storage, nanographene and carbon nanotubes, they enhance the capacity and charging speed of lithium ion batteries and supercapacitors. So solar energy, nanoparticles in solar cells, they significantly increase sunlight to electricity conversion efficiency. Then flexible displays, graphene and silver nanowires, they enable the development of rollable or foldable touch screens. So in flexible displays also, as you can see, there are flexible displays these days for your phone. So there are flexible displays. Then in that, what happens is that graphene and silver nanowires, they enable the development of rollable or foldable touch screens. These are very much in trend. As you can see, certain cell phones, they have flexible displays, foldable screens. So graphene and silver nanowires make that possible by enabling the development of rollable or foldable touch screens. So now they are used in energy generation, thermoelectric, triboelectric or piezoelectric. So they are used in energy generation, in energy storage, supercapacitors and batteries, in energy transmission, insulating material superconductivity, or energy conversions for fuel cells and solar cells. So these are your nanomaterials, 1 dimension, in 2 dimension, in 3 dimension, in different dimensions. All your nanomaterials, these can be used in these applications. Then environmental protection, for water treatment, nanofiltration membranes and antimicrobial nanoparticles like silver and titanium dioxide, these remove heavy metals and pathogens from your wastewater. So your nanomaterials are very vital in the wastewater treatment methods. So the nanofiltration membranes and antimicrobial nanoparticles, these remove heavy metals and pathogens from wastewater. Then for bioremediation, biologically synthesized nanoparticles, they are used to detoxify soil and air pollutants such as organochlorine pesticides. So your nanomaterials can also, they are also capable of detoxifying soil and air pollutants by degrading your organochlorine pesticides. So in environmental protection, your nanomaterials can be used in water treatment and bioremediation very efficiently. So that's your applications of nanotechnology in environment. They can be, your nanomaterials can be used as photocatalysts for breaking down toxic pesticides, antibiotics or toxic dyes in your wastewater. And they can be used in environmental sensing to sense what is present in your polluted water or air or soil. They can be used in environmental sensing. They can also be used as nanofertilizers. Then in energy production and increasing crop yield, antimicrobial, and for absorption, various absorption purposes, for nanoremediation, for membrane filtration and adsorption. So, all these are applications of nanotechnology in our environment. Now, in food and agriculture, smart packaging, nanocomposites improve the mechanical strength. As you already know, they improve the mechanical. So, smart packaging, nanocomposites improve the mechanical strength and gas barrier properties of packaging, while nanobiosensors detect food spoilage or pathogens. So, in both ways, they can also improve your packaging by improving the mechanical strength and gas barrier properties of your packaging material. So, you can use nanocomposites in your packaging material to improve the mechanical strength and gas barrier properties, and also parallelly your nanobiosensors can detect whether your food is okay or it is spoiled. So, your nanobiosensors are going to detect food spoilage or pathogens that are present in your food. So, they can be used as nanobiosensors, and they can also be used in your packaging material. So, they are useful in smart packaging. Then precision farming, nanosensors monitor soil conditions and crop growth, while nanofertilizers and pesticides provide targeted delivery of nutrients and protection. So, they can be used in precision farming. Now, you are not just using any fertilizer in any amount, you are basically doing precision farming. So, your nanosensors are exactly monitoring what your soil requires, what pH it requires. So, they are monitoring your soil conditions for optimum crop growth, while your nanofertilizers and pesticides, they provide targeted delivery of nutrients and protection. Now, application in nanotechnology in food industry. So, they are used in food processing and food packaging. So, that's they can be used as an anti-caking agent. They improve consistency and prevent lump formation. Then nano additives and nutraceuticals, they improve nutritional values of food. Then they can also be used as gelating agents that improves the food texture. Then nanocapsulation and nanocarriers to protect aroma, flavor and other ingredients in food. So, they can be used in this food processing domain. Then they can also be used in the food packaging. They are used in the improved food packaging as use of nanoparticles to improve the physical performance of food. Then in active packaging, nanomaterials can be used as an antimicrobial agent. Or smart packaging, they can be used as nanobiosensors to detect the pathogen present in your food or in your packet. So, that is application in of nanotechnology in food industry. That is nanomaterials in agriculture. So, in crop production, fertilizers, precise farming, nutritional management and soil improvement. That is what I was telling you in my previous slide. In crop production, nanomaterials are very useful. Then in plant protection, for disease management and pest management. For disease management and pest management. Then in nanotechnology, genetic engineering, monitoring and drug delivery. Then in nanobiofarming, usage of remote GPS sensors to monitor the sources. In nanobiofarming, they use remote GPS sensors to monitor the resources. Then nanosensors to diagnose your crop, the soil conditions and whatever environment your crop requires. That is for precision farming. Then stress tolerance, whatever abiotic and biotic including heavy metals. So, that is your assessment of stress tolerance. So, nanocapsulation, pesticides, herbicides and fertilizers, your nanomaterials are used in the nanocapsulation. Then food processing, in food processing and packaging, in food preservation. So, nanomaterials in agriculture, they are used in all these ways to enhance your agricultural output. Then in consumer goods and textiles. Fabrics, engineered nanomaterials, they create stain resistant, wrinkle free and antimicrobial clothing. So, imagine that your cloth is stain resistant, there are no stains on it, something falls on it and it just goes off. Your engineered nanofibers, these are stain resistant, they can be wrinkle free and antimicrobial clothing. So, in personal care, nanoscale TiO2 and ZNO are already used in sunscreens for transparent UV protection. And in automotive, Your nano coatings provide scratch resistance and self-repairing properties for vehicle paints. So, these are nano fabrics that are used to make current clothings, which make your cloth stain resistant, wrinkle resistant, and antimicrobial. So, you can create the super fabric out of nanomaterials. So, nanotechnology is used in textiles for sensing, for antibacterial properties, for water repellency. This can also make it water repellent, like it won't get wet. Owing to the lotus effect, your water droplets are going to fall off from this material. And then flame retardancy, and in UV blocking, and improved dyeability, soil resistance, and anti-static properties. That's nanotechnology in textiles. So, that's the summary. Nanoscale materials, they exhibit unique physicochemical properties, and size and surface effects dominate their behavior. Then emergent optical, magnetic and chemical phenomena arise at nanoscale, and these properties enable advanced nanobiotechnology applications. So, nanoscale materials, they exhibit unique physicochemical properties, as we have studied so far, about quantum confinement, about surface effects, about their super paramagnetism and their unique thermal properties, about their unique optical properties. So, we have studied that so far, and then their size and surface effects that dominate their behavior, which leads to various applications. Then there are emergent magnetic, chemical and optical phenomena. So, these properties basically they enable advanced nanobiotechnology applications. So, summarizing the physical properties, that is surface area to volume ratio. So, as I have already told you, the particle size, as it decreases, the proportion of atoms on the surface increases exponentially. This makes the nanomaterials highly reactive and excellent for applications like catalysis and adsorption. What we studied was melting point depression, that is nanoparticles often have significantly lower melting points than their same bulk material. So, they have for example, bulk gold that melts at 1064 degrees Celsius, while 2.5 nanometer gold particles, they melt at approximately 300 degrees Celsius. So, that goes down to this. So, you can see there is a vast difference in the melting point of gold, bulk gold and gold nanoparticles. So, that is what is known as melting point depression. Then optical properties, what did we learn in the optical properties section? Optical properties are influenced by how nanomaterials they interact with light. So, metallic nanoparticles, they exhibit surface plasmon resonance, where conduction electrons, they oscillate with the incident light and creating unique colors that depend on the particle size. So, semiconductor nanomaterials, they display quantum confinement, confining electrons and leading to discrete energy levels and tunable fluorescence, such as in quantum dots, which change color with size. So, there is a tunable fluorescence in quantum dots which change color along with size. Electrical properties, electrical conductivity in nanomaterials can show quantized conductance changing in defined steps as size decreases. This is known as the ballistic transport. So, I haven't discussed electrical properties in detail as it wasn't required. There is a whole subject on this. So, as the size decreases, this is known as ballistic transport. So, materials like carbon nanotubes, they can also have tunable conductivity, acting as either as metals or semiconductors based on their chirality. Mechanical properties. So, as you have already learned, nanomaterials, they have a low Young's modulus. So, they often have enhanced flexibility and softness due to more surface defects. So, as the surface area is higher, they are more prone to surface defects, and so they have a low Young's modulus, and hence they are softer. So, some ceramics, they can also exhibit superplasticity at nanoscale, which allows for significant deformation. Some ceramics, they can also exhibit superplasticity at nanoscale, allowing for significant deformation. And as you also know, diamond, as you create a diamond nanoneedle, what happens is that diamond is a very hard and brittle material, but if you consider diamond at nanoscale, that is a diamond nanoneedle, it is very soft and it is flexible. So, you can use that for biomedical purposes as a nanoneedle. Magnetic properties, we have already learnt about magnetic properties. The ferromagnetic materials can become super paramagnetic below a certain size. So, what happens is that they lose residual magnetism after an electric field is removed. So, you put an electric field and you remove that, and there is no remnants magnetism and your ferromagnetic material becomes super paramagnetic when you are considering nanoscale. So, which is important for applications like MRI images and drug delivery. So, there's a switch on switch off property at nanoscale. So, now there's no coercivity, there's no no hysteresis loss, and your ferromagnetic material becomes super paramagnetic. So, what is happening is they are losing the residual magnetism after an external field is removed. So, you switch on an electric field and you switch it off, and your residual magnetism goes off just like that. So, this is important for applications like MRI, imaging and drug delivery. So, non-magnetic bulk materials like gold and platinum, these can also show induced magnetism at the nanoscale. So, what happens is that there are certain materials which do not show magnetism when they are in bulk, but when they are at nanoscale, they start to show magnetism at the nanoscale. So, non-magnetic bulk materials also start to show magnetic properties at the nanoscale. So, that is their unique properties, magnetic properties that we have already learned. Then thermal properties, we learnt about some nanomaterials such as carbon nanotubes and graphene that have a high thermal conductivity, which is useful for heat dissipation. So, conversely, increased phonon scattering in other nanostructured materials can reduce thermal conductivity, and this can be beneficial for thermoelectric devices. So, in some nanomaterials like carbon nanotubes and graphene, they have a high thermal conductivity, which is useful for heat dissipation, and what is happening is that this increased phonon scattering in other nanostructured materials, they can reduce thermal conductivity and be beneficial for the thermoelectric devices. Thank you.
This is a very good initiative because sometimes there are topics which we can get tidbits of those from different avenues and on online, on internet. But when it comes to a full course that you can have everything at same place, so that is something which you can get through course on SwayamPrabha, and that is something which I really like about it. And moreover, it's completely free. About this course, I would say that basically starts from the real estate related basics, talks about the structure of real estate, its participant, and then we move gradually to some serious topic regarding the real estate valuation. And from there, we move to certain other areas of advanced real estate concepts. And there are a lot of case studies which we have tried to include so that the real scenarios of what is happening in right now in the market, students can learn through that. Please visit www.swayamprabha.gov.in and explore courses related to your field. Find the appropriate as per your requirement, and please visit so that your learning curves keeps on increasing. Thank you so much.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Today, I'm going to tell you about the different characteristics of the movement of things around the world that are associated with globalization. We refer to these kind of movements as global flows. Now, the concept of global flows is quite important, and it's important for us to understand the different ways in which these flows might occur. Now, typically, when people talk about the movement of things from one place to another in the context of globalization, they're under the misconception that things tend to flow from abroad into the place where they are living. In a very sort of stereotypical manner, there is this idea that with globalization, much of the movement that occurs is from Western countries into non-Western countries. Now, as sociologists, we know that actually global flows are multidirectional. So, which means that as much as there is a movement of flows from Western countries into non-Western countries, there is an equal amount of movement of flows from one non-Western country to another non-Western country, and in fact, a movement of flows from non-Western countries into Western countries as well. Let's take the example of food, for instance. You may be aware of a type of food which originated actually in China and then goes on to Japan, called ramen. For instance, the popular brand Top Ramen that is consumed in India is an example of ramen. Now, ramen, initially the movement is from China, which is a non-Western country, to Japan, which is another non-Western country. From Japan, this very popular food item travels to Western countries such as the US and also more recently to countries in Europe. So there you have a movement from a non-Western country to a Western country. And in fact, now we have very specific types of ramen being consumed in metropolitan centers in India as well. So there's another movement from a Western country to a non-Western country, which is India. So global flows in that sense are multidirectional. A second aspect of global flows is that they could be interconnected. An easy way to think about this would be if you have relatives who are traveling from the US or the UK or Australia, very often you'll see that people request them to carry electronic items with them. They say, oh, can you please get me a laptop, or can you please get me the specific camera lens that I'm looking for. So here you see that the movement of people, which is a person moving from one country to another country, is connected to the movement of technological items as well. So global flows in that sense are interconnected with each other. A third characteristic of global flows is that we could see that they happen in reverse. In fact, they are called reverse global flows. An example of a reverse global flow would be a style of music that you may be very well acquainted with, which is Bhangra. Now, Bhangra music is something that originated, as we know, in the state of Punjab. Now, as you know, Punjab is also a state which has seen a lot of out-migration, not only to other parts of India, but also to other parts of the world. So, as people migrated to other parts of the world, they took their music with them. So, when people migrated from Punjab to the UK, for instance, they hung on to the music that they were familiar with. So Bhangra moved from little villages in Punjab to the major cities where people from Punjab settled to in the UK. While in the UK, over subsequent generations, this music was transformed. It was not only performed in its original version, but it was also performed with the addition of many different types of beats, which are more familiar to people in the UK. At one point in time, you see that this modified form of Bhangra comes back to India. We're talking about the 1990s to the 2000s. So here you see that that a form of music that originated in India moves out of India to the UK. It is modified a little and then comes back to become extremely popular in India again. So in some ways, this form of music is returning to where it started out, but in a slightly changed manner. We call this kind of movement as a reverse flow.